Hi, good afternoon to one and all. I am B. Kaushik of CSC Data Science. My roll number is 24951A6727. Today I came to know incident and adjacency matrices in graph theory. What is a graph? A graph consists of a set of vectors and a set of edges connecting pairs of vectors. Graphs can be directed or undirected depending on whether the edges have a direction. They can also be weighted where edges have values representing cost or distance. Types of graphs. Simple graphs have no loops or multiple edges between the space, same pair of vectors. Complete graphs have an edge between every pair of vectors. Bipartite graphs consist of two sets of vectors with edges only between the sets, not within them. Introduction to matrices in the graph theory. Matrices provide a convenient way to represent and analyze graph mathematically. Two main types of matrices are used: incident matrices and adjacency matrices. Each type of matrix captures different aspects of the graph structure. What is an incidence matrix? An incident matrix represents the relationship between vectors and edges in the graph. The rows of the matrix correspond to vectors while the columns correspond to edges. Entries in the matrix indicate whether a matrix is incident to an edge. Structure of an incident matrix. In a directed graph, the matrix entry is 1 if a vector is the start of the edge, -1 if it is the end, and 0 otherwise. In an undirected graph, the entry is 1 if vector is connected to the edge and 0 otherwise. The size of incident matrix is V by times of V, where V is the number of vectors and E is the number of edges. Example of an incident matrix. Consider a simple undirected graph with 3 vectors and 3 edges. The incident matrix will have 3 rows and 3 columns with 1 second marking incidence. This example helps visualize how vectors relate to edge in graph. Application of incident matrices. Incident matrices can be useful in network following problems and in determining follows problems and determining connectivity. They can also assist in the computation of graph properties such as number of edges connected to each vector. Incident matrices are used in algorithm for graph transfer and optimization. What is an adjacent matrix? An adjacent matrix is another way to represent a graph focusing on connections between vectors. The rows and columns correspond to vectors. The entry indicates whether an edge exists between them. It is a square matrix, meaning it has the same number of rows and columns as vectors. Structure of an adjacent matrix. In a directed graph, the matrix entry is 1 if there is a directed edge from vector to vector x. In an undirected graph, the matrix is symmetric if there is an edge between I and j both are in 1. The size of adjacent matrix is V by times of V. Example of an adjacent matrix. For example, director graph with four vectors, the adjacency matrix can illustrate direct connections. Each entry in the matrix usually present whether there is an edge between specific vectors. This example aids in understanding how adjacency matrices encapsulate graph connectivity. Properties of adjacency matrix. The diagonal entry of adjacent matrix indicates loops. They are 1 if loop exists and 0 otherwise. The sum of each row provides the degree of corresponding vector in undirected graphs. A directed graph without degree and degree can be derived from the sum of the rows and columns respectively. Applications of adjacency matrices. Adjacency matrices are widely used in algorithms for searching and transferring graphs such as depth first search. They facilitate the computation of graph properties like connected components and shortest paths. They are also applicable in network theory and social network analysis to determine relationships. Comparison of incident and adjacency matrices. Incident matrices offers a clear relationship between adjacent and vectors, while adjacency matrices focus on vector connectivity. The size of incident matrices varies with the number of edges, while adjacency matrices are always square. The choosing right matrix depending on the specific properties being analyzed in the graph. Limitations of incident matrices. Incident matrices can between large and unwidely for graphs within many edges. They are less efficient for dense graph where many vectors are interconnected. Analyzing properties using incident matrices may require more complex computation compared to adjacent matrices. Limitations of adjacency matrices. Adjacency matrices can consume a lot of memory for spare graphs where many entries are zero. They do not explicitly represent edge properties such as weights or directions in a straightforward manner. Centering graph operations can be less efficient using adjacency matrices compared to other representations of graph. Beside incident and adjacency matrices, graph can be represented using edge list and adjacency list. Edge lists provide a simple representation but may not be efficient for centering graph algorithm. Adjacency lists save space and can be more efficient for spare graph while still allowing easy traversal. Conclusion. Understanding incidency and adjacency matrices is fundamental for analyzing graphs in graph theory. Each matrices serves different purposes and can be advantageous in specific scenarios. Analyzing graph effectively requires selecting the appropriate representation based on the application's needs. Further reading. For a deeper understanding of graph theory concepts, consider textbooks like Introduction to Graph Theory by Douglas B. West Online resources and academic journal can also provide up-to-date research and applications of graph theory. Engaging in practical projects can further solidify the concepts learn, learned through theoretical study. Thank you.